Hey science fans, welcome back to the lab. Today we're diving into a fascinating topic, circular motion. Get ready to explore the physics of things going around and around. Circular motion is, simply put, the movement of an object along a circular path. It's a fundamental concept in physics that governs everything from the smallest particles to the largest celestial bodies. Think about a car turning a corner, carefully navigating the curve of the road, or consider a satellite orbiting Earth, tirelessly circling our planet. Think about the simple joy of you spinning on a merry-go-round, feeling the wind in your hair. All are examples of circular motion in action, showcasing its diverse applications. It's everywhere, a constant presence in our universe, shaping the world around us. From the movement of electrons around atoms to the majestic dance of galaxies, circular motion plays a vital role. Understanding circular motion helps explain why you feel pushed to the side in a turning car, that sensation of being pulled outwards. It also explains how planets stay in orbit, locked in a perpetual dance around the sun, thanks to gravity and inertia. And it explains why salad spinners work, efficiently removing water from your greens using centrifugal force. Imagine swinging a ball on a string around your head, a simple yet powerful demonstration. The ball traces a circle in the air, a perfect example of the path we're discussing. It's classic circular motion, pure and simple, illustrating the core principles at play. There are specific rules of physics at play, forces and principles that govern this motion. These rules keep the ball moving in that circle, preventing it from flying off in a straight line. We'll explore those rules in detail, uncovering the secrets behind this fascinating phenomenon. We'll journey from the ball on a string to the moon's orbit, examining circular motion on different scales. Get ready to spin your mind around some amazing science as we unravel the mysteries of circular motion. We'll look at why things, according to Newton's first law, want to go straight, maintaining their velocity, and what force keeps them curving, constantly changing their direction to follow a circular path. By the end of this lesson, you'll spot circular motion everywhere you look, in countless everyday scenarios. And you'll know why it happens, understanding the underlying physics that governs this ubiquitous motion. So let's get started. Prepare to embark on a journey into the world of circular motion. First, let's talk about inertia, an object's resistance to changes in motion. If something is still, it wants to stay still. If it's moving, it wants to keep moving straight. This is Newton's first law of motion. In circular motion, an object is always changing direction, so inertia wants it to fly off straight. Cut the string on a spinning ball, and it shoots off in a straight line, thanks to inertia. That's why you feel pushed to the side in a turning car. Your body wants to keep going straight. Objects don't naturally move in circles. They need a force to keep them curving. So, what's that force? Let's find out. Imagine a ball tied to a string whirling around in a circle. What keeps it from flying off in a straight line? The answer lies in a fundamental force. The force that keeps objects moving in a circle is called centripetal force. It's a crucial concept in physics, explaining everything from amusement park rides to the orbits of planets. The term centripetal comes from Latin roots, meaning center-seeking. This perfectly describes the nature of the force. It always pulls toward the center of the circle, constantly redirecting the object's motion. Without this inward pull, the object would simply continue in a straight line, obeying Newton's first law of motion. In our ball-on-a-string example, the string's tension provides the centripetal force. The string is constantly pulling the ball inward, preventing it from escaping its circular path. The tighter the string, the greater the tension, and the faster the ball can spin. If the string breaks, the force disappears, and the ball is suddenly free from its circular constraint, and the ball flies off straight, tangent to the circle at the point where the string broke. This demonstrates that the ball was always trying to move in a straight line, but the centripetal force kept redirecting it. On a grand scale, this same principle applies to celestial bodies. Gravity acts as the centripetal force for planets and moons, keeping them in their orbits around stars and planets. The gravitational pull constantly redirects their motion, preventing them from drifting off into space. Centripetal force isn't a new kind of force in itself. It's simply that we give to any force that keeps something moving in a circle. It's a description of the forces, not its fundamental nature. Tension, like in the string example, gravity, holding planets in their orbits, friction, allowing a car to turn a corner, or even a wall pushing on you in a spinning ride, creating the sensation of being flung outwards. If it points toward the center and keeps the object circling, constantly changing its direction, it's centripetal force. It's the force responsible for maintaining circular motion. Without it, circular motion can't happen. The object would simply move in a straight line, forever. It's the essential ingredient for every spin, every rotation, every curve, orbit, from the smallest moon to the largest planet, and turn, whether it's a car on a racetrack or a figure skater on the ice. That's the cosmic leash at work, keeping everything in its place and governing the dance of the universe. Newton's second law says force equals mass times acceleration. In circular motion, acceleration means changing direction, even if speed stays the same. This constant change in direction is called centripetal acceleration, always pointing toward the center. The centripetal force causes this acceleration. Newton's third law. For every action, there's an equal and opposite reaction. When you swing a ball on a string, the string pulls the ball inward, action, and the ball pulls outward on the string, reaction. There's no mysterious centrifugal force, just inertia and the real inward pull. Newton's laws together explain why things move in circles. Inertia, force, and reaction. It's not magic, it's physics, and it's awesome. All right, let's dive into the fascinating world of physics and get mathematical. We're going to explore the forces at play in circular motion, just like what you experience on a merry-go-round. The key to understanding this is the formula for centripetal force, F equals sine mv2-r. This equation might look intimidating at first, but we'll break it down piece by piece to see what it really means. F, as you might have guessed, is the centripetal force. This is the force that's constantly pulling an object towards the center of the circle, and it's absolutely essential to keep an object moving in a circular path. Without it, the object would simply fly off in a straight line. Next up, M stands for mass. Think of mass as how much stuff is in an object. The heavier the object, meaning the more mass it has, the more centripetal force you're going to need to keep it moving in that circle. It's like trying to spin a bowling ball versus a tennis ball. The bowling ball requires a lot more effort. Now, V represents velocity, which is just a fancy word for speed. But here's the kicker. In the formula, velocity is squared. This means that even a small change in speed can have a huge impact on the amount of force needed. So doubling your speed doesn't just double the force required, it quadruples it. That's because of that squared term. This is why things can get a little wild when you start spinning faster and faster. Finally, we have R, which stands for the radius of the circle. The radius is simply the distance from the center of the circle to the edge. A smaller radius, meaning a tighter turn, requires significantly more force to maintain the circular motion. Think about it. It's much easier to run in a wide, sweeping curve than to try and make a sharp, sudden turn. That's precisely why sharp turns are inherently more difficult to navigate than wide, gentle ones. The tighter the turn, the more your body or a vehicle has to fight against that outward pull. Now, let's bring this into the real world. Imagine you're driving a car and you take a turn too fast. In that situation, the centripetal force required to keep you on the road can exceed the amount of friction your tires can generate. That's where things get dangerous. Engineers use this very formula to carefully design safe roads, calculate banking angles on curves, and even design thrilling but safe roller coasters. It might seem like just a simple equation, but it elegantly explains a vast amount about how things spin, how they turn, and even how planets orbit stars. It's a fundamental principle governing motion in the universe. So, the math behind the seemingly simple merry-go-round is actually a powerful tool that helps us understand and predict how things move, ultimately keeping our world running smoothly and predictably, physics in action all around us. Let's use our formula in real life. Imagine a 1,000 kilograms car driving around a curve with a 50-meter radius at 10 meters per second. F equals sine mv2 plus r. That's 1,000 x 100 divided 50 equals 2,000 newtons. That's the force the tires need to provide to keep the car on the curve. If the road is icy and friction can't provide that much force, the car slides off. This calculation helps engineers design safe roads and vehicles. It's not just numbers, it's the math that keeps us safe every day. From roller coasters to highways, these calculations are everywhere. Physics lets us predict and control motion in the real world. That's the power of understanding circular motion. Velocity and radius are the dynamic duo of circular motion. Increase velocity and the needed centripetal force skyrockets. Increase radius and the force drops. Satellites in low orbits need high speeds to stay up. Those farther out can go slower. On a running track, outer lanes make turns easier at the same speed. On a merry-go-round, standing at the edge means you need to hold on tighter. Your speed is higher, so the force is greater. The interplay between speed and radius shapes everything from sports to space travel. Whether you're an athlete, an engineer, or just having fun at the playground, you're feeling the effects of this duo. It's all about balancing speed and curve. That's how you master circular motion. Science in action. The laws of circular motion apply everywhere, from planets to salad spinners. The sun's gravity keeps planets in orbit. The same math explains a washing machine's spin cycle. In a washing machine or salad spinner, the drum provides centripetal force for the clothes or lettuce, but water escapes through holes because it can't be held in. Centrifuges in labs use the same principle to separate blood components. Roller coaster loops are designed so inertia keeps you safely in your seat at the top. Once you know the physics, you'll spot circular motion in everything from kitchen gadgets to amusement parks. The same rules connect the cosmos and your daily life. Physics is everywhere, big and small. It's not just theory, it's practical, powerful, and universal. That's the beauty of science. We've taken a spin through the world of circular motion. Objects want to move straight, but centripetal force pulls them into curves. The formula F equals sign mv2 plus r explains how mass, speed, and radius all matter. Circular motion is everywhere. Earth's spin, orbits, wheels, fans, and more. These laws help us understand the universe and design our world. From swinging a ball to launching satellites, it's all the same physics. Next time you round a corner or use a salad spinner, remember the science at play. It's not magic, it's a beautiful dance between inertia and centripetal force. Understanding circular motion gives you a new appreciation for how the universe works. Science is all around us.